between the two harmonics. If you increase that, this is shown here, you go, the black curve is just the conventional zero junction. If you increase the second harmonic, you develop this double well. You have a periodic double well potential. So your phase in the ground state can be either at the minus phi or plus phi well. And if you apply a magnetic field, you can tune, you can lift the degeneracy and let's say, decide in which of the two wells you want to prepare your junction. And you can read this out by tilting this potential, this energy, until, let's say here, the minus phi well disappears, and if the particle stays here, it will roll out and roll down, and then you have reached the current. However, if your particle was in the plus phi well, you have to tilt even further until this well also disappears. Here it has not disappeared, and then you have another critical current IC+. So this gives you a Josephson junction with two critical currents, depending from which well you start to escape the particle. And this has also some potential applications where you can write in which phase you want to be and read out by applying current pulses. But I will not discuss this in more detail. Okay, so let me just flash on the summary and take maybe for now some questions. Oh, yeah.
Let's take the moment for questions.
Yeah, that's a good question. Yeah. Yeah, that's a very valid question. So in principle, when you do a measurement, and you want to find out the parameters, what is my critical current? Usually you always have to say what is your voltage criterion. So in practice, when you do a measurement, you can either trace out the IB curve, and you will have some, even on the Josephson branch, you will have some fluctuations. You have some noise from your preamplifier. What you can do many averages. So you measure your IB 1,000 times and average, and then you just set the criterion to be slightly above the fluctuations in the zero voltage state. Typically, in a typical setup, we have a criterion of 1 microvolt. That's a typical criterion you get. Let's say with a standard conventional setup, that's what you get, even without averaging. But yeah, in principle, if you quote some critical current which you measured, you should always say what was your voltage criterion. Yeah. No, we use, we just set, there are more advanced routines where you do extract IC more automatically. Let me see, do I have an IB curve here again? You can, you ramp up your current, and maybe let's say your gamma is 0.01, and now you develop a voltage, and that's what you then define as your IC. But you have to be aware that this is not I naught. This is IC, which is reduced depending how large your noise parameter is. If you really want to get a better value for I naught, you have to run numerical simulations trying to fit your IB characteristics. And then if you get a good fit, you can extract I naught. But this is not so straightforward, because you also, let's say, if you have a non-hysteretic IB curve, you don't know what beta C is. And also beta C changes the shape of the IB curves.
Just a question about switching. So what is normally switching is also causing change, just to measure a jump of to the dissipative branch before the critical current. So it's hard to take out all the noise. This is just thermal noise, but there could be other...
That's an important question when you, if you like to study macroscopic quantum tunneling in these junctions, for example. I guess Francesco will cover this tomorrow. You have to be extremely careful in isolating as much as possible your junction, because any kind of noise will spoil your switching statistics which you are measuring. Yeah. What people do is trying to ramp up the current very fast and do many measurements, thousands or 10,000s of curves to get switching characteristics, but still you get then a histogram of switching currents, and you can then try to fit this to, let's say, if you are still in the classical regime, to some theory, but you always have to be aware that noise can also come from your setup. Yeah. So what people usually do, I'm sure Francesco will show, that you decrease temperature and your histogram gets narrow and narrow. At some point it saturates, and then you have reached the quantum regime, or you have reached the regime where you are limited by your setup. Yeah. And it's just the noise from your setup, and it's not so straightforward to distinguish that. People apply magnetic field to reduce I0, IC, to see whether you can get even lower values of your saturation of the width of the histogram, to make sure that you are not dominated by noise. That's the typical approach.
Okay. So we can continue with the second part, which is about the basics of SQUIDs.
Okay. So we have 50 minutes left, including discussion. So I can skip at the end some applications, so we just can finish in time. Okay. Is it? Yeah. At 1:30. Yeah. Okay, I hope you are not too exhausted by that time. Now I come to one important device which heavily relies on the Josephson effect, which is a superconducting quantum interference device, short SQUID. And if you Google SQUID, you may find also this kind of very nice species, maybe also more commonly known here at the coast. But I will not talk about that. I will talk about this guy here. So it's essentially, so SQUID stands for superconducting quantum interference device. Essentially, it is a superconducting loop, here depicted in blue, which is intersected by one or two Josephson junctions. That's the plan. So I will spend most of the time just on discussing some basics and principle of operation. I will present some practical devices and readout. I probably will skip the readout, and you can ask questions later if you want. And then if there's time, I will just give you some ideas about possible applications of SQUIDs, like magnetometry in biomagnetism or scanning SQUID microscopy. And I should point out, so there is the SQUID. If you would like to look into more details, there are 2 volumes of the SQUID handbook, which appeared in 2004 and 2006, which are collections written by different authors, edited by John Clark and Alex Baginski. And volume 1 is on fundamentals and technology of SQUIDs and SQUID systems. And there is a volume 2, which is on applications of SQUIDs and SQUID systems. So I can recommend those books if you want to learn about SQUIDs in more detail. Okay, I will focus on the DC SQUID, which means the ring is intersected by 2 Josephson junctions. So DC stands for direct current. And so this combines, the SQUID combines the flux quantization in a superconducting ring with the Josephson effect, which I discussed so far. So now we have a spatial interference of the superconducting wave functions in the 2 arms of the SQUID ring. And there's, again, as for the Fraunhofer pattern, which was the analog of a single slit in optics, you have an analogy as a double slit interference in the SQUID. And this gives rise to oscillation of the critical current across this device versus the applied magnetic flux. And I will try to motivate how this comes about. So basically, you start from fluxoid quantization. So again, if you integrate the phase gradient along this dotted path, the integral of the gradient of the phase has to be an integer number times 2 pi. because the wave function has to be uniquely defined. Yeah. And you can do this integration by using the expression for the gauge invariant phase gradient, grad phi, and also the phase difference, which I introduced before. Yeah. And then you integrate from 2 to 1 through the upper electrode across the junction 1 to 1 prime, and then 1 prime to 2 prime in the bottom electrode, and then across the junction 2. And you can just, let's say, plug in the expressions for the phase gradient and phase difference into this equation. You get, as a result, these 4 paths, and then you add them up. And this gives you this expression, and you can rewrite it. And basically what you end up is with an expression for the so-called total flux. This is the flux threading this integration path through the loop, times the integral over the supercurrent density flowing along the integration contour. Yeah. That's the total flux, and on the left side you have internet number times 2 pi. If you have no Josephson junction, okay, you can forget about that, and that's simply the fluxoid quantization in a superconducting ring. Yeah. But if you have the 2 Josephson junctions, you have here the difference of the 2 phase differences across the 2 Josephson junctions. Yeah. So that's basically the fluxoid quantization for DC SQUID. And the total flux you can divide into an applied flux, which from an applied magnetic field, plus an induced flux, which is a circulating current J flowing through the inductance of the SQUID loop. So the loop has inductance L, and you can always separate your currents which you inject, which you send across the device, which goes into the 2 branches, I1, I2. You can always write I1 as half of the injected current plus the induced circulating current, and I2 is half of the injected current minus the circulating current. This means from these equations that circulating current is just the difference between the 2 currents in the 2 branches divided by 2. Okay, and then you can ask yourself, what is the maximum supercurrent across this device? And okay, from Kirchhoff's law, we know we inject the current, and this has to be divided into I1, I2, the 2 branches, and the current through branch 1 has to flow across junction 1, and from that we know via the first Josephson relation that this is I01 times sine delta 1, and the same here for the second junction. So for simplicity, I assume a symmetric SQUID, so their critical current should be identical, I0. And then you, with some trigonometric identities, you can write this as a product of a cosine and a sine function, which contains the phase differences across the junctions. Which then you can use the definition for the total flux to exclude the phase difference of the junction 2. And again, with some trigonometric identities, you arrive at the end at this expression that your current is just 2 times I0 times the cosine of the total flux normalized to a flux quantum times sine total flux divided by I0 plus delta 1, which you still have somehow as a free parameter. And now, in a similar case as for the derivation of the Fraunhofer pattern, you can now try to maximize your supercurrent to find the critical current. For that, you could you could say, okay, I can play here with delta 1 and just set the sinus to 1 by proper choice of delta 1. However, delta, the total flux, which you have also here in the cosine function, is given by the applied flux times the screening flux, and the screening flux contains the screening current, which affects the phase differences. So you have to find the maximum supercurrent. In essence, you have to solve both equations self-consistently, which you cannot do in a very simple way. There were only 2 simple analytic solutions for 2 limiting cases, and one is the case of negligible inductance, and to define this, what is the case of negligible inductance, I have introduced an important parameter for the SQUID, which is the so-called screening parameter beta L. So you can basically you start with what is the possible maximum flux induced flowing through the SQUID without developing a voltage. And this is simply I naught times L. So the induced flux is J times L, and J cannot be larger than I naught, the maximum supercurrent. Yeah. And this flux will never exceed phi naught over 2. Yeah. If this screening flux induces would exceed phi naught over 2, you just change your flux state. This integer number n I derived in the flux quantization by 1. Yeah. And beta L is nothing else than the ratio between this maximum screening flux divided by half a flux quantum. This is the so-called screening parameter. And in essence, it contains the inductance, which means if you have a very small inductance, your beta L will be very small. Okay, in that case, if beta L is very small, the effect of your circulating current on changing the phase difference will be very small. So that means you can neglect the induced flux, and you set your total flux simply to the applied flux, indicated here by the symbol graph. And that means now you are done, because now you have this equation I've shown before, but now I have here the applied flux and not the total flux anymore. And then I can maximize that by simply setting the sine function to 1. And this gives me this cosine type modulation of the critical current, which I showed already in the beginning. Yeah. So this motivates why the maximum supercurrent oscillates. And the period is again like for the Fraunhofer pattern of flux quantum, but this is now the flux applied through the loop of, not in the junction. Yeah. Okay, the other limiting case is the large inductance situation, though beta L is very large. So that means your applied flux can be screened very well by this flux induced by L times J. Yeah. Again, to maximize magnetic energy, you always, L times modulus of J will always be smaller than half a flux quantum. And you can also rewrite this in this way, and by inserting that 1 over beta L is much, much smaller than 1, that means your screening current will always be much, much smaller than I naught. And that means your screening current only weakly changes the phase differences across the junctions. Yeah. And that means that your total flux goes in the step-like case, and this is basically the same as in the Dolnay-Bower experiment for a closed superconducting loop. However, in the Dolnay-Bower experiment, you have always to heat up your device above TC, apply another field, and cool down. Here in the SQUID, you can do this all in one run, because your junction, the phase difference across the junction, can make a phase winding by 2 pi and change the flux state even if you are cold. In that case, the screening current goes just as the applied flux minus n minus phi naught divided by L. And here you see if your L is very large, your screening current will be very small, and it goes essentially to 0 for very large L. And that means you have only a very weak modulation of your screening current, which is just sketched here schematically. And I will not go into details, but one can simply show that the change of IC, delta IC, is roughly given by 1 over L, or 2 over beta L times I naught. And if in the case we are considering large inductance, very large beta Ls, that means if beta L is very large, the prefactor is very small, that is, your modulation is almost much, much smaller than 2 times I naught, which is the maximum critical current you can send through the SQUID. And if you want to do a general case, you have to solve this numerically. This shows IC normalized to I naught, so this is the critical current of one junction, so maximum value is 2, versus the applied flux normalized to the flux quantum, so the black solid trace is a beta L of 0.01, where you modulate all the way down. The dashed line is for beta L equals 1, where you have about 50% modulation of the critical current. And for beta L equals 5, you have much smaller modulation. This simulation is also done for 0 temperature. And you can then simulate this for many values of beta L. This is plotted here on a logarithmic scale. So the normalized modulation IC normalized to 2 I naught versus beta L. And so this saturates for very small beta Ls. You get the full modulation. And if beta L becomes very large, it just scales as 1 over beta L. And let's say this behavior has been already shown in this seminal paper by Claudia Tescher and John Clark at the end of the 1970s. It's also treated in chapter 2 in the SQUID handbook volume 1. You have to be careful. Many people use the modulation depth to extract beta L, and from that, if you measure IC, you get an idea about I naught, then you can extract the inductance of your SQUID. But you have to be careful because this is for a symmetric SQUID at 0 temperature case. If you have an asymmetry in the gradient currents or also in the inductances of the two SQUID arms, your IC versus phi can be significantly distorted. Yeah. And also by thermal noise, this can be significantly changed. Yeah. Okay, let me just explain the mode of operation the typical mode of operation of a DC SQUID. So you send a current, and above the gradient current you develop a voltage. And in principle you could, maybe I should mention that. Now in principle you could use this strong modulation of the gradient current with applied flux to operate the SQUID as a sensitive flux detector. Yeah, so operate the SQUID somewhere here on the steep slope, and you have to you apply a flux change and you move up, for example, here, you detect a change in gradient current. Yeah. But this process takes you some time. It's much, much simpler to operate the SQUID in the voltage state. So I sketch here two IV curves. The blue one for integer number of applied flux, you have a maximum gradient current. If you add half a flux quantum, you have minimum gradient current. And then typically you bias your SQUID at a constant current slightly above the maximum gradient current. And by applying a flux, you move along this line from left to right, so your voltage oscillates with applied flux. And this is shown here. So if you characterize your SQUIDs, you typically measure voltage versus applied field or applied flux, and you do this for many different values of bias currents. If you increase the bias current, as soon as you reach the minimum gradient current, you start seeing these oscillations. At some optimum value, you get the maximum modulation, and if you go up to higher currents, your modulation goes back down again. That's shown here. And now you can use your SQUID as a flux to voltage transducer. So if you apply a small flux signal, your voltage will go up, and you can easily detect that. And certainly important quantity is the transfer function, which is the maximum slope. So your optimal working point would be somewhere here. And the slope tells you how much voltage per flux quantum you typically induce. Typical values are some hundreds of microvolts. And very roughly, this transfer function is given by the resistance of the junction, which means the reverse of the slope of these IV curves divided by the inductance of the SQUID. Okay, one can now model this dynamic behavior if you really like to calculate what will be the transfer function for different types of different value of inductances and gradient currents, for example. The most common approach is again using the RCSJ model to model your two Josephson junctions, which are then coupled by the screening current because you place the two junctions in this loop with inductance L. So you have two coupled equations of motions for the two phase differences of the two Josephson junctions. And they are coupled because current I1 is flowing through the left branch across junction 1. This is total current I over 2 plus the circulating current, as I mentioned before, and I2 is I over 2 minus J. So these two equations of motion are now coupled via this circulating current. So you have to solve both of them together with the condition for the total flux, which is applied flux times induced flux, which is related then to the difference of the phase differences. And finally, you can calculate the voltage taking the average of the changes of the phase differences. Okay, one can do this also taking into account asymmetry of the two junctions in gradient current, capacitance, resistance, also asymmetry of the inductances. I will not bother you with that. I just want to let you know and that this is possible. You come up with normalized equations of motions as I did for the single junction, and then you solve them, and you can essentially simulate all your characteristics. Yeah. Okay. You can also consider this normalized circulating current J over I naught, which contains again beta L and the difference of the phase differences and the normalized flux. This is the applied flux divided by the flux quantum. And if you insert this into the normalized equations of motion, you can again, like for a single junction, write this as an inertial term, a friction term, equaling the derivative of a potential. But this is now a two-dimensional potential because you have two phase differences. And this is the DC SQUID potential, which I normalized here to the Josephson energy. This contains the cosine terms, which are related to the Josephson energy. This term here is due to tilting your potential. But now you also have a magnetic energy, because you have an inductance and you apply a field, you have a magnetic energy. So this goes with the flux to the square, but you also have here this contribution from the phase differences. And
how do you take into account there that it has to be gauge invariant? So there is a relation between the two variables, no? Between delta 2 and delta 1.
But those are both the gauge invariant phase differences already.
Okay.
Yeah. So this has also, I normalized this potential to the Josephson coupling energy. So here the prefect is 1. So basically this term here is the ratio over the Josephson coupling energy divided by a characteristic magnetic energy, which you can write as phi naught squared over 2L. So flux squared over 2L is a magnetic energy. So now you have a second energy scale. That's one important point. And this is just a sketch of your potential. So you have a parabolic shape potential. You still have this wash spot potential along these coordinates, delta 1 plus delta 2, which is that part, along which you are also tilting when you apply a current. And the minimum of your parabola can be changed by applying a flux. And I'm showing here now just top view of the potential, plotting these contour lines for 0 applied flux and half applied flux. And the dashed line indicates the trace your particle would run down once you apply a tilt, once you apply a current here. And at 0 applied flux, the trace is just a straight line. However, if you apply half a flux quantum, your minima shift between these rows of neighboring minima and your particle traverses in this meander-like trace. Okay. Okay, a few words on, we still have 30 minutes, including discussion, good. A few words about noise, because if you want to characterize the sensitivity of the device, you will, at the end, ultimately limit it by the intrinsic noise of your SQUID. So I mentioned you measure a voltage across your device, which tells you how much flux change you coupled into the SQUID. But you have this resistors at finite temperature, you have Nyquist noise, and you will have at least some thermal noise. But you also have some recurrent fluctuations, which gives you rise to 1 over F noise. So you have, in addition to the DC voltage, you have some noise voltage, which has some spectral power density of voltage noise, which I denote as SV of F. And this noise voltage via the transfer function V phi, you can write as an equivalent noise flux. So you can use this. You have a noise flux, and this noise flux is given by the noise voltage divided by the transfer function. And that's why you can also come up with an equivalent spectral density of flux noise as phi, which is just the voltage noise power divided by the transfer function to the square. So that's typically in a measurement, you measure the voltage noise, you take a Fourier spectrum to measure, make a Fourier transform to measure get the voltage noise spectrum, and then you divide by the transfer function square to get the flux noise of the SQUID. Typically, the RMS flux noise is quoted the square root of S phi, and this is then given typically in units of flux quanta per square root hertz. And this is a typical measurement showing RMS flux noise in units of microphi naught per square root hertz versus frequency. And you get typically a thermal white noise coming from Nyquist noise from the shunt resistors, and 1 over F noise, which can come from discrete current fluctuations. It can also come from motion of vortices, which are somehow trapped in your SQUID ring structure. Okay, and for completeness, you can also define a fluctuation energy, which is the noise flux to the square divided by 2L, and you can define an energy resolution epsilon, which is the flux noise power divided by 2L, and this is typically given in units of joule per square root hertz. Okay, we discussed the noise surrounding of the current voltage characteristics. If this noise parameter gamma is large, and yeah, basically you can state that thermal fluctuations at finite temperatures become important when KBT approaches the Josephson coupling energy. So if KBT is coming close to the amplitude of the washpot potential, and that means you somehow destroy the Josephson coupling by thermal fluctuations. But now we have a second